Uh, Hello everyone. I hope I'm audible. If it is possible, please confirm anyone if whether I'm audible or not and my video is visible or not. You can write in message also. Am I audible? Okay. I I hope I'm audible, and if my audio is not clear, you can ask me. So I'll try to rejoin and fix it. And so welcome everyone to this tutorial of the Advanced Linear Algebra course, NPTEL, NPTEL course, and this is tutorial 4. So in today's tutorial, we will mostly discuss the matrix representation of a linear transformation and linear functionals and dual of a vector space, finite dimensional vector space mostly. Good evening. I'm audible, right? So today is 14th February. Okay. So as the previous class, so in today's video also what I'll do, I'll try to solve some problems and which may help you to solve the upcoming assignments. And during that those problems, when I will try to solve those problems, and whatever the theorems is needed, I'll try to explain or at least try to state clearly and try to explain a little bit, which may help you um, to understand more clearly. Okay. So let's start with a problem. So I hope no problem is clearly visible. Um, so what the problem statement says that if T be a linear operator on R3 defined by this way, like T A B C sending to the vector A plus B, B minus C, comma C, and let this is a particular ordered basis of R3, order basis of R3, okay, and then which of the following statement is or are correct. So now look at carefully. Their order basis in general for R3, one of the basis is like 1 0 0 0 1 0 and 0 0 1, something like that. But here it is not like that. Here order basis is something a little different. Okay. So here the order basis is like 1 0 0 1 0 1 1 and 1 1 1, and this is the ordering. Okay. Now so with respect to this ordering, so we have to try to find which of these are correct actually. Yeah, which of these are correct. This is the what it is asked. Which of these are correct? Okay. Sorry. So look at carefully here. One, it is asked the matrix representation of T with respect to this order basis. So at least one of them will be correct. At max one of them will be correct, and another is these two. T is not invertible and something like that. So first try to find the matrix representation of T with respect to this order basis. Okay. So with respect to this order basis, how one can write ABC with respect to this order basis. So look at carefully. If you want to get A in the first place, at least you have to multiply A with this vector. Okay. So 1 1 1. So that's why we will write 1 comma 1 comma 1, and this is the E3 last vector. So one can write it as E1 E2 E3. This is the three vector. And now if you, so now what you are getting in the second place, in the second place you are automatically getting A. But if you want to get in the second place B, so then you have to multiply with this, that B minus A into 0 comma 1 comma 1. Okay. And so now what you are getting in the first place you are getting A, and second place you are getting B minus A plus A, that is B. In the third place you are getting B minus A plus A, that is B. But you want to get in the third place C. So that's why what you have to do, you have to multiply C minus B. Yeah, C minus B, it will be A, B minus A, yeah, C minus B whole into 0 comma 0 comma 1. So this is the, then also you can check that this is correct. Okay, C minus B into 0 0 1 and B minus A 0 1 1 and A 1 1. So that means with respect to this order basis, matrix representation of, or one can say that if we write beta is the order basis, this 0 comma 0 comma 1, this is E1, 0 comma 1 comma 1, this is E2, and another is 1 comma 1 comma 1, this is E3. So then this ABC matrix representation or coordinate vector of this is like C minus B, B minus A, A. Okay. So now you have this expression. Okay, sorry. Okay, let me keep this. Or maybe you don't need this, but I have to find the matrix representation of T. So let's start with the order basis with respect to this order basis. So what it sends 0 0 1, where it sends 0 0 1 to 0, B minus C, that is minus 1 C1. So with respect to this decomposition, if I want to write ABC in terms of this, what it will be, C minus B, that is minus uh, where it is sending B001, it's sending 001 to C minus B. So C is 1 and B is 2. So 2 times 0 comma 0 comma 1 plus B minus A is 0 and B is minus 1. So minus 0 comma 1 comma 1 plus A. So this is what it is. And T is sending. So therefore the matrix first column of the matrix representation of T with respect to this order basis will be 2 comma minus 1 comma 0. This is the first column of the matrix. And now T sending the entry 0 comma 1 comma 1, that is the second entry, where it will send by the formula A plus B, that will be 1, B minus C, that will be 0, and C, that is 1. So according to this formula, that according to C minus B comma 0 0 1, so what it will be, C minus B is actually 1. So I will not write 1. So 0 comma 0 comma 1, this is the first vector. B minus A, that is minus 1, and 0 comma 1 comma 1, and A, that is 1 comma 1 comma 1. So this will be like 1 minus 1 1. So this is in the column vector with respect to this order basis. Column vector, it will be 1 minus 1 1. Okay, and now what it's sending 1 comma 1 comma 1, this will be like according to the formula A plus B, B minus C. A plus B is 2, B minus C is 0, and C is 1. So how to express this with respect to this order basis, this 0 0 1. So C minus B, that is 1. So this will be 0 comma 0 comma 1 plus B minus A, that is minus 2 B minus A, yes, that is minus 2 0 comma 1 comma 1 plus A plus 2 1 comma 1 comma 1. So this will be like 1 minus 2 2. This is the matrix representation. So let me check which matrix it is matching. This is exactly matching the second option. Okay, so that's why option B is correct. So if option B is correct, option A can't be correct, because matrix representation is unique with respect to a fixed order basis. If we change the order basis, matrix representation may change, but we are in a specific fixed order basis, so that's why matrix representation will not change. So that's why this option is incorrect, this is correct. Now let's check for the other two. Now question is T is invertible or not. We know that T is invertible or not, that depends whether determinant of the matrix representation of T is non-zero or not. Okay, I let me just I have said many things, but before that I should have said this thing. Um, suppose V be a finite dimensional vector space with an ordered basis. Ordered basis is very much required here. Ordered basis beta, which is equals to consisting alpha 1, alpha 2, alpha n, where n is equals to dimension of the vector space V, then matrix representation matrix representation of a linear operator T from V to V is given by T. This is written by this way. This is the matrix Aij, where, so this is like this is the matrix. It is sending ij1 to n. This is the matrix. Ijth entry of the matrix is Aij, where how this Aij are related, that T of alpha j, this should be summation of Aij alpha I, sorry, not alpha, yeah, alpha I equals to 1 to n. So this is the matrix representation. I am using those things here. Okay. Now other two option, what it is asked, that T square is equals to T, and second is asked that T is not invertible or not. So if you check carefully here, what it is giving, that T of A, B, C, this is equals to A plus B, comma, B minus C, comma C. So now assume this is mu A dash, B dash, C dash. Now T square of A, B, C, what it will be? It will be T of A dash, comma, B dash, comma, C dash. So according to the formula, what it will be? A dash plus B dash, and A dash plus B dash is actually A plus 2B minus C, and B dash minus C dash, that will be B minus C minus C minus 2C, and C dash is C. So this is what it is, T square. But this is obviously not exactly equals to T of ABC. You can choose ABC such that these are not equal. So that's why the third option is also not correct. So now what it remains, the final option, whether this is correct or not, T is invertible or not. So now it is known that a linear operator, this is very much standard, but even if you are not able to understand why this is standard, so you can ask, I'll try to explain. Linear operator T on a finite dimensional vector space V is invertible if and only if it satisfies some relation, if and only if the matrix representation, the matrix corresponding to T with respect to any ordered basis, any ordered basis, with respect to any ordered basis is invertible. So what I am trying to say here, suppose you have a linear operator on a vector space to vector space to vector space, and V is finite dimensional vector space. Okay, finite dimensional is required. So otherwise you will not get the matrix representation. That's the main problem. So suppose you have a linear operator from a finite dimensional vector space to finite dimensional vector space. So now the question, when a linear operator is said to be invertible, if there exists another linear operator A from V to V such that TA is equals to identity is equals to A TA. This is what it is. That is what is called linear invertible. And we already stated in the previous tutorial that a linear operator is invertible on a finite dimensional vector space if it is either bijective or injective or surjective. If it is injective, it automatically becomes surjective. Injective means 1 1, and if it is surjective, then it automatically become 1 1. That is equivalent to the fact that T of alpha is equals to 0 implies alpha equals to 0. Okay, but that fact is equivalent to that if we are taking an ordered basis of the vector space V and try to find the matrix representation of the linear operator T with respect to that ordered basis, whatever the matrix it will be, if that matrix is uh, invertible, then T will be invertible. Okay, but when a matrix will be invertible, if the determinant is non-zero. Okay, so now what we got here, T is the matrix representation of T is this. So let's check whether whether this is the second option. So whether this is invertible or not. So that means determinant is non-zero or not. The matrix representation of T, recall, that what I have written later, that equals to 2, 1, 1, minus 1, minus 1, minus 2, 0, 1, 2. This is what it is, the matrix representation of T. But the question is whether this matrix is invertible or not. That means determinant is non-zero or not. So let's check what is the determinant. So determinant of this is equals to 2 into minus 2 minus minus plus, this is 0, minus 2 plus 2 minus 1 minus 2 and plus 1 1 minus 1. Okay, so this will be 2 minus 1 1, which is not equals to 0. So therefore T as an operator, as a matrix, is invertible, which implies T as an operator is invertible. But what is option asked? This is what is the option stated? What is the option stated? T is not invertible. So that's why this option is also incorrect. So is there anything you have not understand in this problem? Anything, any very simple or not able to catch due to some problem, whatever I'm trying to say, or any terminology which is not clear to you, you can ask. I'll try to explain again. In this problem, if you have any other doubt, anything regarding this problem. So I hope it's clear. Even it is not clear, I have starting the new problem. Even if you are not able to understand anything, you can let me know. I will try to go back and try to explain that problem. So let's go back to a new problem. So what the problem tries to say here, first let me understand that. So let V be the space of all polynomials of degree less than equals to 2. So that means V is a vector space of dimension, V is a vector space of dimension 3, because constant 1x x square. Okay, and this is what it is given with the order basis of V. And let Qx is a polynomial 2 plus 3x plus 4x square, and D be the differential operator. This is given like this one. Where now here it is giving dq is a vector, d is a differential operator from the vector space V to V. Okay, that means d maps p to p dash. This is what it is. P dash is the derivative with respect to x. Okay, so that is dp dx. This is the derivative. Now this is what it is means. Dp box means the matrix representation of dp or coordinate vector of dp with respect to this order basis. Okay, and q be and matrix giving. So it is said that if dq, the coordinate vector of dq, is equals to q into coordinate vector of dq with respect to another order basis beta dash b dash, then what is b dash? This is the question. So what is the question? We have dp, p is a polynomial given fixed, okay, and the matrix representation of dp with respect to order basis b, I'll write this as b, is actually equals to q into matrix representation of 2 with respect to some another order basis b dash, another order basis b dash, and q is this matrix. Then other order basis of b dash, what is the other order basis of b dash? This is what we have to find. What is the other order basis of b dash? So what you know, first let me explain an statement or theorem or some, you can say some fact, at least it's true. So what is the fact says, let V be a vector space and beta finite dimensional vector space. V be a finite dimensional vector space, finite dimensional vector space, and beta is equals to alpha 1 all the way alpha n, where is an ordered basis of V. Here n is actually the dimension of the vector space V. Okay, so now what is the and let beta dash is equals to alpha 1 dash all the way alpha n dash be another order basis of V, then if alpha is in as is a general vector in V, then as we know this is a basis, so alpha can be written in terms of linear combination of some vector alpha I equals to 1 to n. Then alpha with respect to this order basis is a column vector like x1, x2, xn. Now assume alpha being a vector in V being an element in V, and beta dash being another order basis, alpha also can be written in terms of xi dash, alpha I dash, and let's assume the coefficients are xi dash I equals to 1 to n. Then alpha, coordinate vector of alpha with respect to this new order basis is x1 dashed all the way xn dashed, and we will denote this x and denote this x dash. Now as I have said, so what is the relation between these two coordinate vector? Okay, suppose you have a fixed vector and you are expressing that vector with respect to two different order bases. Okay, so now so there must be some relation. Okay, so what is the relation between x and x dash? That relation is x is equals to p x dash, where P is the matrix Pij, which is given by something like that, where Pij is something like that alpha j dash is equals to summation of Pij alpha I equals to 1 to n. This is called basis change matrix. So that means this fact says that any vector alpha with respect to this order basis B is equals to P into alpha with respect to order basis B dash. So here is also we have asked the similar thing and given the matrix Q. And this is a one fact what I have said, that if you have a vector space B, we have two ordered bases, then how to change this ordered basis and how to coordinate vectors x and x dash, how x and x dash are related. But question is, suppose we have in other around. Okay, other around means, so what is other around I'm asking? What other around I'm asking? I'm saying, suppose you have a invertible matrix. Suppose you have an invertible matrix P. Here the starting point is that two order basis is given. Suppose we have an invertible matrix P, invertible matrix. We need invertible matrix, square matrix, obviously square matrix, and invertible n by n square matrix, and we are giving an order basis alpha 1, alpha 2, alpha n. Then how to get the other order basis? The other order basis like this way one can get. So conversely, if P is an n by n invertible matrix, then there exists, or you can study conversely, here I can, if beta is equals to alpha 1 to alpha n be an order basis, and if P is an invertible n by n, then there exists another order basis, there exists an order basis alpha 1 dash alpha n dash, such that for any alpha in the vector space V, coordinate vector of alpha with respect to beta is equals to P into coordinate vector of alpha with respect to beta dash. And in that case, alpha j dash is equals to summation of P of ij alpha I equals to 1 to n. So therefore the main point is that if you have a matrix, you can easily get the another order basis. Okay, so here what is the matrix giving? Matrix is giving Q, and what I have said, this fact is true for any vector alpha in the vector space, right? So here D is a differential operator and Q is a special entry, right? But that special does not going to give you anything extra, but you can do without that various extra thing. So what is that Q here it is giving? Q is this, so let me write this Q and the order basis. So here beta is giving, so in our case beta is giving like 1x x square, and Q, which is P actually, that is the matrix, Q is the matrix 1 1 1 0 1 2 0 0 1. This is the Q. So now this is assumed alpha 1, alpha 2, alpha 3. Now we want to find alpha 1 dash, alpha 2 dash, alpha 3 dash such that dp whole with respect to b is equals to q with dp with respect to b dash. We want to find this, right? So but it's roughly enough to say finding alpha 1 dash, alpha I dash is something like alpha 1 is equals to uh, alpha j dash is equals to what it will be summation of q ij I equals to 1 to 3 here alpha I, this is what it is. So let me, so basically what I will get that alpha 1 dash that is equals to this with respect to uh, qij, j is fixed, so 1 is the here, so this is the first column, so this will be 1 here. Alpha 2 dash is equals to j is 2 right now, so that means the second column I is 1 to 2 because yeah, I is 1 to 2 because this is 0, this is going to be 0, so this will be 1 plus x, and similarly alpha 3 dash will be 1 plus 2x plus x square. So this is the basis 1 plus x, 1 plus 2x plus x square. So this is the correct option 1 plus x, 1 plus 2x plus x square. So I, is it clear, or should I explain anything which is not clear to you? You can ask even a very simple question, that's not a problem. I will try to explain. So here what I just try to say that here D and Q is not any special terms, not any special thing which may give you something very special. That's okay. So I hope it is clear. Even if you have any doubt to the regarding to the previous questions or these questions, or not able to understand anything to the course, or any problem you start, you can ask. I will try to explain that. You can ask anytime in between the, even if I'm solving any other problem. So let me go to the another problem. So what this problem says, let me read this first. So let T be a linear operator, sorry, let T be a linear operator on F3 cross 1. Okay, that means the column vector, yes, column vectors. And the Tx is equals to Ax given. And A is this. That means the linear operator is given by matrix here. It is. So that means this is the matrix representation of the linear operator T with respect to standard ordered basis. This is what it is called. But here we are giving something new, that delta, this box which I will denote by b and this by b dash, beta dash. So let beta is equals to 1 0 0 column vector, alpha 2 is equals to 0 1 0, alpha 3 equals to 0 0 1, all of them are column vector, and beta dash consists three vectors, the 1 0 0 1 1 0 1 1 1, ordered basis of f3. So let alpha be any element of F3 cross 1, and with matrix represent coordinate vector of alpha with respect to this second order basis is actually x dash, and with respect to the first order basis with x. Then which of the following statement is or correct? So here we already clear that x is equals to, here it is giving x is equals to b and x dash is equals to alpha b dash. That, so to the previous from the previous, for any alpha, this is for any alpha, okay. So previous discussion says that if P is the basis change matrix, that is, okay, so okay, let me, the basis change matrix that is P, that is alpha j dash is equals to Pij summation of alpha I equals to 1 to n, okay. Pij summation of I equals to 1 to n, Pij alpha I, okay. So for all I equal, for j equals to 1 2 all the way 3, here it is n, we can write, that's not a big deal, okay. So then this is the matrix representation, right? So Okay, so this is what it is. So then we know that x is equals to px dash. Okay, that we know. So x is equals to px dash. This is both in the both case, but p is the, so in the first two option x equals to p dash written, but p, two type of p is giving. So we have to check what is the p. Maybe one of them are correct, maybe none of them are correct. Okay. So what is the p? P is the basis change matrix. Okay. So here let me clearly mention alpha 1, alpha beta is equals to alpha 1 alpha 2 alpha n, that is alpha 1 alpha 2 alpha 3. This is equals to, in order basis, 0 1 transpose, that is column vector, or I can write in column vector also that 1 0 0, this is first, second one is that 0 1 0, and the third one is that 0 0 1. So you can clearly look at the standard order basis. This is called standard order basis. And px is equals to ax, then A is the matrix representation of T with respect to the standard order basis. This is very standard thing. Even if you're not able to understand anything which I'm saying, very easy, you can ask. I'll try to explain that. Okay, it's not a problem to asking anything. Okay, to the with respect to the standard order basis. Okay, so this is beta, and what is the beta dash? Beta dash was column vector 1 0 0 1 1 0 and 1 1 1, and clearly one can note that 1 0 0, which is actually alpha 1 dash, which is equals to alpha 1. So this will give the first column of p, so p will be equals to 1 0 0, and second one is that 1 1 0, which is equals to alpha 2 dash, which is equals to clearly alpha 1 plus alpha 2, which gives the second column of the p. Third one is that 1 1 1, which is actually clearly alpha 3 dash, and which is clearly alpha 1 plus alpha 2 plus alpha 3, which is equals to 1 1 1. This is the matrix. Okay. So therefore P is the this is matching with this. So first option is correct, and P is unique matrix. When a basis change we are doing, that matrix is completely unique, invertible matrix. So that's the second option is incorrect. Now it is asked matrix representation of T with respect to the first order basis is actually A. Okay, this is what I'm trying to explain here. Okay, it is clear. Note that beta being standard order basis, T with respect to B is actually A. Now where it is asked what is T with respect to B dash is equals to, this is what it is the question. Here B dash is this new vector, new basis. Okay, this is the question. So there is very standard fact that if you have two bases, alpha 1 alpha 2 alpha n, just in general fact. So fact is that, so T with respect to this new order basis is equals to P inverse T with respect to B and P. This is what it is. So how this is very easy thing, very easy to check. You can look at from here. Suppose you want to get the matrix representation of T with respect to the new order basis beta dash. Okay, so that means you want to write that. So what is the matrix representation of a linear operator? The matrix representation of a linear operator with respect to any basis B or B dash is equals to matrix representation of, matrix representation is actually the matrix. If you write B, that is equals to the matrix of T with alpha with respect to B for all alpha belongs to the vector space B. This is for any standard order basis B is true. What it is means, for any alpha in V, T alpha, T is a linear operator. Actually, this is true for linear transformation. T is a linear operator from V to V. Suppose you are taking a vector alpha from V, you get T alpha that is coming from V. Now, as T alpha is in V and you have a ordered basis in V, so T alpha can be written in terms of B, that will be some vector, that will be some column vector. that is some coordinate vector. Now that coordinate vector, the matrix of T is actually that matrix, a matrix such that that matrix will be something like alpha with respect to B. If this happens for all alpha, then that is the matrix, and that matrix can be obtained by using the standard order, using any order basis you can obtain. So here is the standard thing. So now for any alpha you will get this one. Okay. So in particular what you will get, T alpha with respect to another order which is B dash is actually T B dash with matrix representation B dash. Okay. But also we know that that any vector alpha in B, for any vector alpha in B, alpha with respect to B is equals to P into alpha with respect to B dash for all alpha belongs to B. So that means in particularly this is true for T alpha. So that means T alpha B can be written P into T alpha B dash. But T alpha B dash is actually equals to T B dash alpha B dash. And another way, T alpha B is equals to T B alpha B. Okay. And alpha B is equals to T, this is equals to T, this is equals to TB, alpha B is equals to P into alpha with respect to B dash. That is Ax equals to Px dash. This is what it is. So now, as this is true for all alpha, so you can take alpha order basis, then what will get TBP as a matrix P TB dash. So that means TB dash is equals to P inverse TBP. So in our case, we have to find, we know what is the P. P is this matrix, right? P is this matrix. So in our case, P is equals to 0, I think 1 1 1 0 1 1 0 0 1. I think this is P, right? This is what it is, P. Yeah, this is P. So we have to find P inverse basically. So what is P inverse? So let's start with finding the inverse of this matrix. So determinant is 1. So we have to take adjoint, I mean cofactor thing. So let me do the inverse. This will be, first term will be 1 minus 0 1. Second term will be minus this and this. Second term 0. This will be 0 corresponding to this term. This will be 0 again. Now corresponding to this term, this is minus plus minus plus minus. 0, it will go like minus, it is right. So this will go minus 1 1, this will go 1 1, yeah, this is 1 plus, because 1, this is minus corresponding to, so this will be like this is 0. The next is like 0 corresponding to 0, minus 1, because this is plus minus, yeah. So this will be 1. So this is the P dash. So that means we have to find 1 minus 1 0 0 1 minus 1 0 0 1. This is P dash into that T with respect to new order basis is equals to, and the matrix of T with respect to the order basis, that is a standard 1 4 3. I'm writing from so the matrix 1 4. What was the matrix given? 1 4 3 minus 1 0 2 3 2 1. This with P 1 1 1 0 1 1 0 0 1. This is what it is, P. So let me do the multiplication. So first I'll do these two. So what I'll get, 1 minus 1 0 0 1 minus 1 0 0 1. So this is something like writing 1 5 8 minus 1 minus 1, yeah, minus 1 plus 1, sorry, minus 1 plus 2, that is 1. That means that minus 1 minus 1 minus 1 minus 1 minus 1, yeah, I think I'm writing correctly. Okay, minus 1 plus 2, that's 1. So 3, 2, 1, that is 3. 3 plus 2, 5, and this is 6. So basically, first column will be as it is, second column will be addition. So 4, 5, minus 1, 5. Third column will be addition with the all of them. So 8, 1, 6. This is correct. So now let's do the another multiplication. This with this, 1, 1, 2. This with this 5 plus 1, 6. This with 8 minus 1, 7. Is it matching with someone? 1, sorry, 8 minus 1, 7. Is it matching? 1 plus 1, 2. 5 plus 1, 6. Yeah, it's matching. Matching. Okay, so 0, 0, 1, minus 1, minus 3, minus 4. Okay, this will be 0, minus 1, minus 5, minus 6. Yeah, it's still matching. 0, 1, minus 6, minus 5. Yeah, it's matching. So 0, it will be 3, 5, 6. So yeah, it actually matching with the third option, 2, 6, 7, minus 4, minus 6, minus 5, 3, 5, 6. Yeah, this is the third option. So you can look at carefully, 2, 6, 7. This was the option. So this automatically will be incorrect because there will be exactly one. Okay, there is no more extra. So this is what it is. So I hope it is clear. This is just simple calculation. It is little longer. You can do it quickly. I mean, if you want to do, but there is a risk that if you try to do any quick calculation, there will be little bit possible of mistakes, and that may take longer. So that's why it's better to always do simple calculation very simply. Okay, so is there any doubt regarding this problem or any previous problem? Anything not able to understand or anything have any confusion? The theory matter which I have tried to explain or start to state. Okay, so I'm going to the next problem then. So this is the next. This is another problem. So what it says that consider a linear transformation T from R3 to R3 such that the matrix representation of T with respect to the ordered basis this is A is equals to this. Then which of the following statement is or are correct? Okay. Linear transformation T such that the matrix representation of T with respect to the ordered basis this is A. Then which of the following statement is or are correct? Okay, sorry. Let's see. Linear transformation T such that the matrix representation of T with respect to the order basis this is A. Okay. Matrix representation of T with respect to this order basis, this what it is, beta is equals to or whatever it will say. Let's assume this is as beta is A. Then which of the following statement is or are correct? So now, so so what we know, let, and this is very standard that we know that if T is T matrix representation we have, let V be a finite dimensional vector space, and dimension of V is actually n, and let alpha 1 all the way alpha n be an ordered basis of V, be an ordered basis of V. Then what we can say is that T alpha for any alpha belongs to, then for any alpha basically this will be like for any alpha in V, T alpha with respect to this ordered basis beta, which I'll call beta, is equals to matrix representation of T and alpha with respect to beta. This is what it is. So now, so if I want to say where it is asked something like this, here it is asked something like this, right? So we have to find matrix representation of for corresponding to alpha equals to 1 0 0 2 1 minus 1 0 1 1 and 2 1 minus 1, whatever it is. Okay, so now here it is given that TB is equals to the matrix A. Okay, so now in particular, if we take here it is, if you look at carefully, here four vectors are given: 1 0 0, 2 1 minus 1, 0 1 1, 2 1 minus. Actually, three vectors are given: 1 0 0. It is asked to find. We have to find T alpha beta for alpha is equals to 1 0 0. This is first. Another is 2 1 minus 1. This is second. Another is 0 1 1. This is third. So look at carefully. Already 1 0 0 and 0 1 1, they are already member of this order basis. So that's very standard. And so what is the matrix representation of TB? TB is the matrix representation. Its ijth entry or the column, jth column is actually the matrix representation of T alpha j. Sorry, column vector. I mean, if basically matrix representation, if we say what is TB, TB is equals to A is equals to, if I write Aij, then basically what I am writing, T of alpha j is equals to summation of Aij alpha I equals to 1 to n. This is what I have said. That means corresponding to, if we map alpha j under T, then whatever the coordinate vector of alpha j, that will be the column vector, jth column vector. Coordinate vector of T alpha j will be the jth column vector of the matrix representation of T. So therefore, here in order basis, 1 0 0 is actually in the third position. So that means the matrix representation of T alpha, that is T 1 0 0, that will be the third column. So third column is 0 3 2. But this is not matching. This is written 0 minus 3 minus 2. So that's why this is not correct. Okay. And similarly, let's check 0 1 1. 0 1 1 is the second one, so that will be second vector, that is 1 1 0, but it is 1 minus 1 0. So that's why this option is also not correct. So now obviously there is two more options, but both of them are asking the value of T at the point 2 1 minus 1. So 1 will be correct. So let's check what is the correct option. So I hope this is clear. What I'm trying to say here is that if you have a linear operator T from V to V, and if you have a order basis like beta, alpha 1, alpha 2, alpha n, then the matrix of the T is something such that if we express T alpha j in terms of this order basis, whatever it is, that Aij alpha I equals to 1 to n, so then the coordinate vector of T alpha j with respect to this order basis is actually the jth column. So this way we are getting the matrix representation of T. So as you have here, here we have the basis elements 1 0 0 0 1 1. They are elements from the basis. So that's why we don't need to do anything extra. But you have 2 1 1. So here is the pain that you have to first express 2 1 minus 1. I think this was the vector in terms of this order basis 1 0 0 2 1 minus 1 0 1 1. So let's write this vector. Actually, this is column vector. But okay, let me write this way: 2 1 1. Sorry, not 2 1. 2 1 minus 1. This is equals to like A 1 0 0 plus B. We have to first express. I have to first express this vector with respect to this order basis alpha. Sorry. No, sorry. I am written little wrong. So the order basis is 1 to 1. Yeah, sorry. So alpha 1, alpha 2 is a little different. Yeah, sorry. So alpha 1 is equals to 1 to 1. This is the alpha 1. Alpha 2 is equals to 0 1 1. And alpha 3 is equals to 1 0 0. Okay. Okay. So it will be like A into alpha 1, that is 1 2 1, plus B into alpha 2, that is 0 1 1, plus C into alpha 3 1 0 0. Okay. This will be like A plus C, and this will be like 2A plus B, and this will be like A plus B. Okay, A plus C, 2A plus B, A plus B. I think this is correct. So this has to be equals to 2 1 1. So what we'll get, A plus C is equals to 2, 2A plus B is equals to 1, A plus B is equals to minus 1. So how to solve this? So from these two, what I'll get, If I subtract it from the first to last, so what will get C minus B is equals to 2 minus 2 minus minus 1, that is 3. So what will get C is equals to B plus 3, that I'll get. Good. Now if I replace that C is equals to B plus 3 there, so what I'll get, A plus C is equals to A plus B plus 3 plus 3 is equals to 2. So what I'll get, A plus B is equals to minus 1, and another one is that 2A plus B is equals to 1. So if we subtract it, what I'll get, this is minus A, which is equals to minus 2. So A is equals to 2, and B, what I'll get, B, so A plus B is equals to minus 1, so B I will get is equals to A plus 1, sorry, B I'll get, B is equals to minus 1 minus A, that is minus 3, and C I'll get B plus 3, that is equals to 0. So C is 0 and A and B is 2 minus 3, so therefore, so the fact is that the coordinate vector, so 2, 1, minus 1, this vector with respect to this order basis, actually A is 2, B is 3, minus 3, and C is 0. This is the coordinate vector. So this will become here alpha beta, right? This is the alpha beta. So here matrix, so T 2, 1, minus 1, this with respect to beta is equals to matrix representation of T, which is actually, what is the matrix of T? Where is the matrix? 2, 1, 0, 2, 1, 0, minus 1, 1, 3, minus 1, 1, 3, 0, 0, 2. This is the matrix with respect to the basis 2, minus 3, 0. Okay. So this will be like 2 plus 2, 4, minus 3, 1, minus 2, minus 3, minus 5, minus 5. Okay. Minus 5 and 0. So this I believe second one. Yeah, second one. So this is correct, so this is incorrect. So I hope this is clear. If there is any doubt, you can ask in this problem or any previous problem or any material, or even my screen is not visible in that purpose. Yes, yes, yes. 2, 1, minus 1. This is alpha, right? This is alpha. 2, 1, minus 1 is the alpha. First, we have to express alpha with respect to the ordered basis given here. And what is the ordered basis here given? 1, 2, 1, 0, 1, 1, 1, 0, 0. So here is the hmm? So the coordinate vector of alpha is coordinate vector of alpha with respect to this order basis is this 2 minus 3, 0. Okay. Right, right. T alpha beta for this. So here 1, 0, 0 and 0, 1, 1 already being in the basis, this is clear. That's why I have already mentioned this thing. So only it left for 2, 1, 1, 2, 1 minus 1. That I'm trying to do from here. I mean, we have to find it. They are not basis. Here alpha not basis. Here what is asked, I mean, I'm summarizing these questions, these options. The summarizing to this option is that we have to find T alpha with respect to the coordinate vector of T alpha with respect to the order basis B and beta, when alpha is equals to this. Okay, na? This is not order basis, so even if it is still making any confusion, so let me change the language. We have to find T alpha T um, alpha. I should not write. So let me change it. T alpha for when alpha is any of this. Alpha is this or this. Alpha is this. They are not set. alpha is this. Yeah, I hope this is clear. So this should not look like an basis. So okay, so even if anyone have any other problem, you can ask. Or this one also, even you are not able to understand, you can ask. So I hope my screen is visible. I mean, smoothly visible, not any pause or anything. If there is any pause or visibility problem, you can ask. Or okay, so I'm going to another problem. So which of the following statement is or are correct? So here can be more than one options, but we are always assuming more than one option is there. So if W is subspace of R7 such that dimension of W is equals to 3, W is the intersection of three hyperspaces in R7. So what is hyperspaces? First question. I think this is the first question. What is the hyperspaces? And another term is the linear functionals. So, so what is the hyperspace? First, let's try what is the linear functional. So a linear functional. So here I need a little bit of theorem. A linear functional let V be a vector space over a field F, then a linear functional F from V to F, the field F, is a map satisfying satisfying the property F of C alpha plus beta is equals to C of F alpha plus F beta for all alpha. Beta is coming from the vector space V and C is actually scalar that is coming from the field F. So basically what it is saying, a field over itself is a vector space, one-dimensional vector space. So a linear functional is actually nothing but a linear function is actually nothing but a um, linear operator from the vector space to the underlying field. This is what it is. So a linear function is nothing but a linear transformation from the vector space to the underlying field. Now, so here, if the f is non-zero, if f is non-zero, then dimension of range space of f must be at least one. Okay, dimension of the range space of f must be at least one. But here the codomain, which is actually f, that is one dimensional space. So that's why that is, but f as a vector space is one dimensional over f. So that says range is actually full. That means f is surjective. That says range of f is full. That is f is surjective. So what we obtain here, a linear functional, a non-zero linear functional is always surjective. That's very standard. Actually, why non-zero? Because if you non-zero, that means there exists at least one element in the domain such that f maps that element to the non-zero element. So as f is a linear transformation here, so that therefore f will map 0 to 0. There is no doubt about this. F always maps 0 to 0 because f is a linear transformation and a linear transformation always maps 0 to 0. So now if f is non-zero, that means f maps some non-zero entry to some non-zero term. Okay. So in that case, range is full, that means linear functional. So now if V is finite dimensional, then kernel of f, that means all those vector alpha belongs to V such that f of alpha is equals to 0, is a subspace of V. Achha, here is one thing here, then achha, here is so kernel of f is always a subspace of V. Now if V is finite dimensional vector space and the dimension of V is actually n, then by rank nullity theorem, what we get? Rank of f plus nullity of f, that has to be equals to dimension of V, which is actually n. But range space has dimension 1, that's clear. If f is non-zero, I'm taking f is non-zero, so that's why. But rank of f, that is equals to 1, that says nullity of f, that must be equals to n minus 1. So what we got or obtained, so nullity, what is nullity? Nullity means the dimension of the kernel of f. So that says kernel of f is a, kernel of f is an kernel of f is an n minus 1 dimensional subspace of V, and this fact is true for any linear functional. Okay. And what is the hyperspace? Hyperspace is actually any vector. I mean, if you are taking a vector space, finite dimensional vector space, then any n dimension is n, then any n minus 1 dimensional subspace of V is called hyperspace. Let V be a finite dimensional vector space over a field, whatever it is. But the field is always fixed, that f. Okay, vector space over a field f, and dimension of V is equals to n. Then any n minus 1 dimensional subspace of V is called hyperspace, or sometimes called hyperplane, though they are okay, hyperplane. So what I'm trying to say from this linear functional and hyperspace, that every linear functional, if you have a non-zero linear functional, you will get a hyperplane, that is nothing but the kernel of f, and vice versa is also. If you have a hyperplane or hyperspace, you will get a non-zero linear functional. Okay, so that is, this is a fact. If we have a non-zero linear functional on a finite dimensional vector space, for a finite dimensional vector space V, finite dimensional vector space V, if we have a non-zero linear functional, then if we have a non-zero linear functional, then we have a hyperplane or hyperspace. Conversely, if we have a, I am not proving, one side is clear. If you have a non-zero linear functional, you will get a hyperplane. That is what I have said. But if we have a hyperplane, from that, why you will get a non-zero linear functional, that I am not proving. But that is also very 2-3 liner proof. You have to span that space, and that's all, nothing else. I mean, something like that. Okay, let me write this. If we have a linear functional, if you have a hyperplane, then we will get a linear functional. Actually, how this fact, if you have a linear functional, you have a hyperplane, that's clear, because you will take the kernel of that. Okay, conversely, suppose V is a vector space and dimension of V is actually n. I'm roughly this is saying, W is a subspace of V, subspace, and the dimension of W is actually equals to n minus 1. So let us take alpha 1 all the way alpha n minus 1 be an basis of W. So that means if I want to get the basis of V, we can extend that basis. So how one will get able to extend? We have n minus 1, we will write one more basis. This is the suppose extension, and this is be a basis of V. Now let us define a linear functional from V to W such that this will V to F such that this subspace W will be 0. Will be null space. So how one will write? Suppose you have this vector xi alpha I equals to 1 to n. So what I have to write? I have to write just only xn. This is what it is. That means F is mapping the last coordinate of the coordinate vector. For every alpha belongs to V, what I will get? For every alpha belongs to V, alpha has a uh, linear expand. Alpha has a suppose I am taking this is the ordered basis. So this is ordered basis I am taking x equals to 1 to n. So in that case, f being linear, f will map something, but what I will map? F should map this vector to the last xn. So then if you look at carefully, any vector which is in W, that must go to 0, because if any vector in W, that should not have the alpha n coordinate vector, because any vector in W actually spanned by this alpha 1 to alpha n minus 1. So there will not be any coefficient corresponding to alpha n. That's why any vector in W must go to 0. So this is a linear functional, one can easily check. Then f becomes a linear functional. One can check that f is a linear functional and W is actually the kernel of f. So from starting from a hyperplane, you are getting a linear function. Okay, that's not the important thing, but these are the little bit of theorems. So but here is here we need actually more. So here is one theorem is needed. If you insist, I will try to explain. Otherwise, I'm writing that statement. So theorem. So how does hyperplane things are connected? So that's the main target, to write this statement. If W, if let V be a, so two theorem. Let me write that two theorem. Then okay, but before that, I need to write one more terminology, that is annihilator. Let W be a subset. We can take subspace also. Subset. I'm taking subset. So you will get the subspace thing is also true, subset of V. Then okay, but before that, I need to say another thing also. Let V dashed. Okay, note that set of space of all linear. If you recall one thing from the last or second last class, that second last tutorial, I have tried that if V and W are two vector space, then the set of all linear transformation from V to W, that will forms again a vector space over the same field here, and the dimension of this vector space is actually equals to dimension of V times dimension of W. Okay, so now, so here if we, as I have said, the linear functionals are nothing but the space of all vector linear transformation from V to F, the underlying field, and field has dimension 1 over itself. Okay, then space of all linear functionals is denoted by V star. This is called dual space, and dimension of V star is actually same with dimension of V. Because of this fact, dimension of W is 1 here. Okay, so that's right. Dimension of equals to, this is the first fact. Another fact is that so V star is actually key. V star, so V star is actually all linear functional. F from V to underlying field such that F is linear. This is what it is, V star. Set of all linear functionals. Okay. Now annihilator means for a subset W of V, annihilator of W is denoted by W is denoted by W naught, which is actually giving by collection of all those f in V star such that f should map all the entry 0 for all W belongs to capital W. So that means that is collection of all linear functional whose kernel contains W. This is what it is I'm trying to say, that all those linear functional which should map the kernel and W entry to 0. So though here we don't have any connection, right now we don't see any connection with the hyperplane or hyperspace, but there is a connection that I'm trying to explain. If you are not able to understand, you can try to, and not, this is also not much required. In fact, this is required for your purpose. Per problem you need only statement, but it's better to know because these are the conceptual things. So W naught is equals to, this is what it is. So this will form a subspace. This will always will form a subspace. So theorem says, one of the theorem is that, important theorem, if V is a finite dimensional vector space, and W be a subspace, here I am taking subspace, then subspace of V, obviously subspace of V, then dimension of V is equals to dimension of W plus dimension of W naught. This is a very interesting and important theorem. So this theorem actually will help to say that any k dimensional subspace, this is another theorem, any k dimensional subspace W of V with W of V and dimension of V is actually n, then W is intersection of n minus k hyperspace or plane, hyperspaces in V. Basically, if you look at carefully how this theorem, I'm not going to prove, but I'm trying to explain how this statement you can connect at least. If you know, that's good, but if you not able to recall or not known, then so suppose W is dimension of k, then what is the dimension of W naught? That is equals to n minus k, right? And W naught means collection of all those functionals which sends, for which W is actually in their kernel. So that means W is actually inside the intersection of kernels of all those entries in W naught, and kernels of all those entries in W naught is actually our hyperplane. But I mean, the fact is that, so from here you can say that W is actually subset of intersection of kernel of F, where F is coming from W naught. But this kernel of F, they are hyperplanes. So that means this is inside the intersection of some hyperplanes. But W naught is also a subspace, as I have said, and dimension of W naught is actually n minus k. So that means W is actually sitting inside the intersection of n minus k hyperspace. That's clear. But this is not making sure that W is actually exactly equals to, but that will be, you can give some argument. I mean, argument is very much in front of us. We have to, that if W is not exactly equal, so we can go to a contradiction. But this is the something what I'm trying to connect, trying to explain, that how to connect that dimension of W is actually n minus k, And W naught says that W is actually inside the kernel of all the entries in F W naught. So that means W is actually inside the intersection of kernel of F, and F is coming from W naught. Now, as kernel of F are hyperspace or hyperplane corresponding to each linear function F in W naught, so that means W is actually inside the intersection of kernel of W naught. And other way, that why I am saying this is exactly subset, but why this can't be proper, or sorry, why this can't be proper subspace, that's the another thing, but this is subspace. That's very easy, but I am not trying to explain this. So these are the things. So these are the two theorems which you need, that V is a vector space and W is subspace of V. Then dimension of V is actually dimension of W plus dimension of W naught. Another W naught is the annihilator, and another thing is that any k dimensional subspace, suppose W, is actually the intersection of n minus k hyperspace in V. So I hope I am able to explain how the hyperplane, how the linear functional connects, and how this statement is actually making sense, or how one can explain this statement. Actually, this is what I'm trying to say. So if this terminology are okay with, then let's go back to the problem. So the problem is not very much easy from those two statements. So what is the problem says? So let's get back to the problem. So which of the following statement is or are correct? So what are the statements? If W is a subspace of R7, so V is actually equals to R7. So that means dimension of V is actually 7. First, dimension of W is actually 3. Okay. Then W is actually intersection of 3 hyperspace. That's not clear. So that means if dimension of W is equals to 3, then W is intersection of 7 minus 3, that is 4 hyperplane. So that's why this statement is, first statement is not correct. But parallelly, if you look at the, and this statement is equivalent to this, that W is subspace of R7 such that dimension of W is equals to 3, then W is the intersection of the null space, of 3 linear functions. Linear functional, as I have said, linear functional actually one correspondence with the hyperspace. Okay, non-zero linear functionals. So as here it is saying, the last option is saying W is in the intersection, W is the intersection of the null space of 3 linear functionals. So that's is the same statement with the first. As first is not correct, fourth is not correct. Okay. Now let's get back to other statement. Every hyperspace is the null space of linear functional. That what I have already proved. Obviously here I have to write non-zero linear functional, but that is understandable that it is considering non-zero linear functional. Third option. If W is subspace of R7 such the dimension of W is equals to 3, then W is the intersection of 4 hyperspace. This is also correct. So is this problem clear to you? If there is any doubt, just let me know. Anything you have not understand properly, even the theorem or statements what I have tried to explain. If you are not able to understand proofs, that's okay, but try to connect things. At least that those things you should remember and how things are going. Okay, just 1 second. So I hope this is clear. So let's go to the next problem. And once again, if you have any other problem to the previous problems what I've tried to discuss today, and any other problem from the previous class or previous from your lectures you can ask. Not able to understand from there. Okay, so let's get back to the new problem. So this is another problem, and this is another new style problem. So we need new theorem once again. So what it says, let V be the subspace of R4 spanned by vector beta 1, beta 2. Regarding the annihilator. So once again we need annihilator, all those things. Let V naught be the annihilator of the space V, and what it is says, V is actually span of beta 1, that is 1 comma 1 comma 0 comma 1, and beta 2, that is 0 comma 1 comma 0. Okay, and V naught is the annihilator. Okay, all those linear functional on R4 such that which takes this to 0, and have a basis G1 G2, which is the basis. This is what it is. The question says V is a subspace. Actually R4 is the main vector space, and V actually the subspace which is spanned by these two vectors. Okay, they are obviously linearly independent, but even they are dependent, that does not matter. That's not going to help you anything. So let the annihilator of V naught. So it's clear here, as they are linearly independent, what I'm saying, that means right now dimension of V is actually 2, and the dimension of the main vector space, that is 4. So now there is a formula, the dimension of V is equal to dimension of W. So let me change it to W and W naught. W and W naught. And this is what it is, V. So let me write, this is W naught. So this is W, okay? So now here dimension of W is 2. So therefore dimension of W plus dimension of W naught is equals to dimension of V, which is actually 4. That states that dimension of W naught must be 2. But here it is asked that those two, G1, G2, for which this holds. But we will try to explain some little different way. So what is the general form of a linear functional? Okay. So okay, let, okay, I have tried to let f from V is here R4 here, V any R4, that doesn't matter, V to f be a linear functional. If here is a theorem, you can say alpha 1 to alpha n, if let's take dimension of V is n, okay, obviously finite dimensional, we are completely in finite dimensional, dimension V is equals to n, and let beta, which is actually the order basis I'm writing, alpha 1 all the way alpha n, bn ordered basis of V, okay. Then for any alpha is actually in the vector space V, alpha can be written in terms of xi alpha I is equals to 1 to n, and x1 x2 xn column vector is the coordinate vector for the vector alpha. But if I want to obtain f alpha, what I will do? Due to linearity, I can write xi f alpha. So basically, if I know what is f alpha, then we know what is the f of alpha for any vector alpha, right? This is what it is. So let f of alpha I is equals to ci for I equals to 1 to n. Okay. So whenever you have a fixed order basis and whenever you have a linear functional, you know these are what these are. This is what is the f alpha is are actually. So now this can be written as ci xi. So what I have tried to explain is from here is that any linear functional must be look like this way, where xi are actually where x is equals to x1 to xn is an ordered basis. Sorry, is coordinate vector of alpha with respect to some order basis. So in our case, ordered bases are standard. There is no nothing. Order basis, no, not order bases are not standard. Order bases are standard. So in our case, order bases are standard. So order bases are not important. So main fact is that any linear functional should be look like this way. Okay. So now, so as we are in R4 and here nothing mentioned, so they are order basis basically. So basically, what I'm trying to say, that says that if x1 x2 all the way xn, this must be equal to summation of ci xi for some ci, for some constant ci. This is what it is I'm trying to say. So now here we have two vector. So what I want to obtain? We want to obtain W naught is equals to all those linear functional from V to W, V to the field F, which is actually R here, such that F of W is equals to, or F of beta I is equals to 0, where beta I is equals to beta 1 is equals to, there two vector is there, 1 1 0 1, 1 1 0 1, and another is that beta 2 is equals to 0 1 1 0. I think these are the two vector, 1 1 0 1 0 1 1 0. Okay, now what I want to say is that, so as I have said, I have to find all those linear functions. So let's try to find a general linear functional. Okay, so as I have said, so general linear, so this is how a general linear functional should look like. This is how a general linear functional should look like. Okay, this is what the general functional should look like. So now, so here beta x1 x2 x3 is this. So therefore if f is equals to this, so that says that c1 plus, that implies c1 plus c2 plus c4, that is equals to 0. Another is that c2 plus c3, that is equals to 0. Is it clear? Because here I have taken, these are the x1 x2 x3 x4, and this is once x1 x2 x3 x4. Then this is giving from where f of beta 1, that is equals to 1 1 0 1 is equals to 0, and another is that f of 0 1 1 0, this is equals to 0. These two is giving this two set. Now if I can solve this c1 c2, then whatever the possibilities of this solution, they will provide you a linear functional, because whatever the choice of ci, they are ci, I mean set of ci, c1 c2 cn, they will give you a new linear functional. Okay, so that means whatever the linear functional will be, they should satisfy these two conditions, that c1 plus c2 plus c4 equals to 0 and c2 plus c3 is equals to 0, where c1 c2 c3 are the coefficient of x1 x2 x3 x4. Okay, so let me come here. So what is the, so necessary condition is that if gx is equals to summation of ci xi, then we should have c1 plus c2 plus c4, this is equals to 0, and c2 plus c3 is equals to 0. And these are the necessary conditions. And how one will get? Here you have two independent variable, c3 and c4. One you have to take c3 0, c4 1, and then you will automatically get c1 c2. And once you have to take c3 1, c4 0. Yeah, I mean c3 c4 interchangeably 0 1, you will get two solutions. These are the two solutions. You can solve that way also. You can do that way also. Now c1 is 1 here, c2 is minus 1 here, and c4 is minus 1 here. So 1 minus 1 is not 0. So that's why first option is not correct. And second option you can check also. You can check from here is also okay. Here let me complete this then from this way. So if we take, if c3 is equals to 0, c4 is equals to 1, that gives c2 equals to 0, c1 is equals to minus 1. So this gives a linear solution, fx is equals to c1 is minus 1 minus x1 plus x2, 2 is 0, plus x4, this is another. And if I take c3 is equals to 1, c4 is equals to 0, then what I will get? c2 is equals to minus 1, and once c2 is equals to 1, c1 is equals to 1. So this will give fx is equals to x1 x1 minus x2 plus x3, and these are the two linear functional, and they are linearly independent. These are the two facts. If you scalar multiply this linear functional, and if you scalar multiply this linear functional, 1 minus 1 2 3 4 5 anything, so any real number, any irrational number, doesn't matter, you will get the same linear transformation. But these are the linear, so these are the independent, linearly independent linear functional. So g1x is equals to minus x1 plus x4 comma g2x is equals to x1 minus x2 plus x3 are two linearly independent linear functional. Linearly independent linear functional. So you will automatically look at that these are the option is there. So, and another way you can say that you have to satisfy these two conditions, whatever way you can look at. So first one is not correct. So you can from there, what are the options, that x1 minus x2 plus x3, x1 minus x2 plus x3. So this is also same, minus x1 plus x2 minus x3, and x1 minus x1 x4. So second option is the correct, because this is actually whatever we obtained, this is the minus one multiplication, so not they are not different. First fact. Second fact is that uh, this is what it is exactly matching, but if you look at, this is first one is matching, but the second one is not matching. This is also not matching, this is also not matching, so the other two are also incorrect. In fact, you can check with this that c1 plus c2 plus c4 is equals to 0 and c2 plus c3 equals to 0, but you have to be careful that c1 c2 c3 are actually coefficient of x1 x2 x3 x4 respectively, so you can check. So is this problem clear? Even if you have any doubt here, you can try to, and I'll try to explain if you can say. Okay, so let's go to the another problem. So here is the problem. If be the subfield of C, okay, sorry, this is what it is. So what if the question says let F be the subfield of C? You can assume F is complex. That's separate. That's not going to bother you anything. Now the question is here here Fk x1 x2 xn is like look like this way. For all k from 1 to n, and let n be the linear functional, these are the n linear functional, then the dimension of the subspace annihilated by f1 f2 fn. The dimension of the subspace annihilated by f1 f2 fn is actually, so here it is asking dimension of the space that is x1 x2 xn such that in overall fn such that fi x is equals to 0 for all I equals to 1 to n. This is what it is for I given, where fi x1 x2 xn is actually equals to summation of k minus I, this is fk, k minus I xi I equals to 1 to n. So this is also the same way whatever I have tried to, I mean nearly same way, they are not exactly same way. Suppose you are, suppose, I mean just for the sake of completeness, I will prove this one with little bit different way, but let me tell you which are the very efficient one way at least to solve, but maybe that this problem maybe not able to solve that. Suppose we are giving f1 f2 fn. Suppose we are giving fi ax is equals to summation of ai fjx, which is equals to f, no they are row, so fi suppose we are giving fi, yeah, fix is equals to aij xj, j equals to 1 to n, for all I equals to 1 to some m. Okay, suppose we are giving like this way. Okay, so obviously m is less than equals to n, this is less than equals to n. There is a reason, because I mean reason is not necessary, otherwise there will be what is called inconsistent, consistent, those things will come, but here it is, whatever it is. But the thing is that, so if you have this way, so here thing is that we have to find all those x for which this fi x is equals to 0. That means you can write it as a matrix. So that means that is summation of aij xj j equals to 1 to n equals to 0 for all I equals to 1 to m. We have to find all those x, right? This is what it is asking. So basically, if I write the m by n matrix, this is m by n because m number of row is there, and this is what it is, x1, x2, xn is equals to 0. So basically, we have to find, that is, we have to find dimension of x belongs to Fn. I'm just for general sake of generality I'm writing, such that Ax is equals to 0, where A is equals to Aij. And you know how to do that. That already discussed in. So basically, how to get that dimension of x? Basically, kernel of, here it is once a kernel of the. So that will be basically, then if you do the row reduction with the matrix A, then this will be exactly actually the dimension of the, sorry, this will be the number of zero rows. This will be exactly the number of zero rows. Yeah, this will be exactly the number of zero rows. This is what it is. Okay. So so but here I will try to solve a little differently, that I am saying. So you know how that's what I'm trying to say, is actually the generally how to solve. But here, if you look at carefully, here we have some pattern. So we'll follow that pattern, and then it will become very easy. So fkx is actually summation of k minus I equals to 1 to n, and xi, right? So we can write it as summation of k into I equals to 1 to n minus I into, sorry, minus summation of I equals to 1 to n. So let us take two linear functionals specific, that g1 is equals to summation of xi. So this can be written, first of all, this can be written k into summation of I equals to 1 to n xi, and this is what it is already written. This is something I'm writing in little different way. So this is for all k equals to 1 to n. These are the things. So basically, if for all k equals to 1 to n, these right hand side terms are actually fixed. So let g1 x is equals to summation of xi, I equals to 1 to n, and g2x, that is equals to summation of ixi, I equals to 1 to n, are two linear functional. So basically, any fk x is actually k into g1 minus g2x. This is what it is we are getting, right? This is what it is we are getting. So now, so that is what I am getting. That is kg1 x is equals to g2x for all k is equals to 1 to all the way in, right? Now, in particularly what I will get. So suppose we are taking 2k, for example, 1 and 2. Okay. So here already taken. That's the important thing. Here n greater than equals to 2 taken. So as n is greater than 2, for any 2, as n is greater than equals to 2, then take k is equals to 1 and k is equals to 2. Then what I'll get, that g1x is equals to g2x for all x. I mean, we have to find those x for which this happens. Another is 2g1x is equals to g2x. So basically, we have to find x belongs to the field Fn such that this holds, such that above things holds, such that above thing holds. So what I'll get here, that g2x, g2x, make it that g1x will be either 0 or this will be exactly 0, not either 0 or 1. This will be 0. g1x is equals to 0. Okay. That says summation of g1. What is summation of xi? Sum g1x, that is equals to xi equals to 0. This is the first condition, I equals to 1 to n. Okay. Another condition is that, at g1x is equals to 0, that says g2x is equals to 0. That gives summation of ixi is equals to 1 to n equals to 0. So basically, therefore, we need to find the dimension of the space, all those x1, x2, xn coming from the field f n, such that summation of xi is equals to 0, summation of ixi I equals to 1 to n is 0. Here is also I equals to 1 to n 0, and that is n minus 2. First of all, why this? Okay, here is two facts I should make it clear. First of all, why this space has dimension n minus 2? This is the first question. Why this space has dimension n minus 2? Because here, if you just don't give any condition, like summation xi equals to 0, summation ixi equals to 0, if you don't give any condition, then dimension is n. But when you give two conditions, that means dimension will be reduced by 2. Why? Because those two conditions will help you to reduce those two dimensions. Basically, what I'm saying, you can express any two term with respect to any two term with respect to n minus 2 terms using these two equations. This is what I'm, if they are linearly independent, and they are linearly independent here. Okay, as these two equations are not scalar multiple of one another, so that's why the dimension, these two equations will help to reduce two dimensions. Basically, what I'm trying to say is that, for example, suppose you have this condition. So that means if you know x1, x2, xn minus 1, if you know this, then you know what is xn. That is to minus x1 minus x2 minus xn minus 1. That means that will help you to reduce one dimension. Similarly, now you don't need xn. So that means dimension reduced. So now suppose you are using, you know what is xn and you know what is x1, x2. So for example, and now if you replace like this way, here only, then that will also reduce one dimension. This is what I'm trying to say. So here, how to do that? That if you know x1, x2, xn minus 2, for example, this is what it is. It will be better. If you know x1, x2, xn minus 2, n minus 2, then if you replace them, x1, x2 all the way, this xn minus 2, then these two equation will give xn and two equation in xn and xn minus 1, right? Because there is two equation, these two equation will give you two equation in xn and xn minus 1, and you can solve those two equation and you will get the solution. So that means for the solution, you need the linearly independentness for this n minus 2 value. So that means this dimension is n minus 2, and why the kernel as actually this space. This is another fact what I am trying to explain. That is, you have to find all those x for which fkx is equals to 0. So now if g1, g2, whatever we have discussed this way, so that says we have to, so basically you have to find all those x for which these two holds, that k g1x equals to g2x for all k equals to 1 to n. Okay. Now, if these two holds, so necessarily we will obtain that g1x is equals to 0 and g2x equals to 0. Conversely, if g1x equals to 0, g2x equals to 0, then we will say that automatically these two holds. And if automatically these holds, then automatically fk, so basically here what I'm saying, actually, we have g1, gx. So basically x belongs to fn such that fkx is equals to 0 for all k is equals to 1 to n. This is same with x belongs to fn such that k g1x is equals to g2x for all k is equals to 1 to n. These two set are equal because these two set are equal. What I've said, yeah, these two set are equal. This is and this set is actually same with x belongs to fn such that g1x is equals to 0 and g2x is equals to 0. This is what it is, the last one, this last expression. Why this is? Because if you know that if fk is equals to 0 for all k equals to 1 to n, that will force that for all k g1x equals to g2x, okay, and that will force that if g1x equals to 0, g2x equals to 0. Conversely, if g1x equals to 0, g2x equals to 0, you will automatically get k g1x equals to g2x, and that will automatically give you the fkx equals to 0. I hope this is clear. I know this is a little bit different from the previous whatever we have done, but this is interesting questions. So dimension is n minus 2. All other options is incorrect. So is it clear? Or if you have any doubt, you can ask. I will try to explain it more because this question is a little different. Okay, I hope it's clear. If it is not, even you can ask, not a problem. Okay, let's go to the next problem. I hope that will be the last problem for today's. Dual basis. Here it is asked to dual basis of this basis. Same problem. I have tried to explain the previous one. Previous one. The same thing. These are the duality. That's why it is called dual. So what it is says, suppose we have R3. Okay. So let me state it what it is. We have R3, that is the vector space, and beta is actually the basis is 1, 2, 0, 0, 1, minus 1, and 2, 1, comma 1. These are the three vector and they are in the basis. This is what it is. And this is ordered basis. Ordered basis, I'm taking this is the ordered basis. Now, dual basis of this is actually all those f1, f2, f3. What is the dual basis of a basis? So if alpha 1 all the way alpha n be an ordered basis of V, dimension of V obviously n, then there exists a basis f1, f2, fn of V star, that is the dual space, with the property fi alpha j is equals to delta ij, that is Kronecker delta, that is equals to 1 if I not equals to j, sorry, I equals to j and I equals to j, and 0 if I not equals to j. And this is very much clear. Suppose you have a vector space V and you have a basis consisting elements alpha 1, alpha 2, alpha n, right? So now you have V star. V star is the space of all linear functionals on V. Now, if you want to obtain the basis dimension of the actually basis or dimension is n. That's clear because of the fact that dimension of L space of all linear operators from V to W is actually dimension of V times dimension of W. That will force you to the dimension of V star is actually n. I have said it in the beginning of this today's tutorial. So, but if I want to get a basis, special basis, which is connected to the alpha and alpha to alpha n, so this is one of the basis. So we are defining basis like this way. F1 is something which will be 1 at the 1 and all other entries it will send to 0. All other basis element, that order basis element will be 0. So in this way, any linear functional, so here is the duality. So here is an interesting fact, duality. Any linear functional f in V star must be of the form f is equals to summation of f of alpha I, f I equals to 1 to n, and note that alpha 1, alpha 2, alpha n are the basis element and fi is its dual basis. Okay, and any alpha belongs to the vector space V must be of the form alpha is equals to summation of fi alpha alpha I. This is what it is called duality. So duality, I mean, this may be not maybe not required for this problem, but I'm just setting for this one. This is very interesting. Why this is dual basis is saying, because if you have a basis alpha naught to alpha n for a order basis of a vector space V, you can get an order basis f1, f2, fn of V star, which acts like this way. You are obtaining f which involves alpha I and fi, completely clearly known right now. Okay, and you are obtaining alpha which is involving fi and alpha I and completely known. So this is what is the duality. Maybe we don't need duality, but this is what it is. So this is what it is, dual basis. So now, so how to get the dual basis? If I, so here it is given ABC is equals to given. So let me first then find. So we know what is F1, F2, F3 on alpha 1, alpha 2, alpha 3, right? Alpha 1, sorry, we know what is F on alpha 1, alpha 2, alpha n, and what is alpha 1, alpha 2, alpha n. This is alpha 1, this is alpha 2, this is alpha 3, but we don't know this alpha 1, alpha, F on any element ABC. So let's first try to find what is on an element ABC, and that will be exactly the answer. So for any ABC, I have to write this in terms of x1, what was the alpha 1, alpha 2, alpha n. Alpha 1, alpha 2, alpha n is actually 1 to 0, right? 1 to 0, 0, 1 minus 1, yeah, this was right. 1 to 0 plus x2, this is 0, 1 minus 1 plus x3, 2, 1, 1. This is what it is. So I have to find x1, x2, x3. So let's find, that's little tricky, x1 plus x3, comma 2x1 plus x2 plus x3, comma minus x2 plus x3, and this is equals to ABC. That will give me that x1 plus x3 is equals to A, and 2x1 plus x2 plus x3, that will give me B, and minus x2 plus x3, that will give me C. So if you use the fact that x1 plus x3 is equals to A here, so what I will get, x1 plus x2 plus x1 plus x3, and which is actually A, plus A is actually B. So what we got actually, that says x1 plus x2 is equals to B minus A. And here we have minus x2 plus x3, so x3 is equals to x2 plus C. So if you replace this in here, so what will get, x1 plus x2 plus C is equals to A. So x1 plus x2 is equals to A minus C. Sorry, I have made some. X3 is equals to x2 plus xc, that's true. If you replace x3 is equals to this, so what help I may get? 1 to 0, 0, 1 minus 1, 2, 1, 1. So there will be minus, only one minus, right? Yeah. x1 plus 2x3. Yeah, this is the mistake I'm making. This is 2x3. x1, sorry. x1 plus 2x3, 2x1 plus x2 plus x3 minus x2 x3. So this is 2x3, x1 plus 2x3. So then calculation will change a little bit. So everything will change a little bit. So we have this fact. So So let me obtain what is x3 here from here. X3 is equals to x2 plus c. Now replace this here. What will get x1 plus 2x2 plus 2c is equals to a. That is x1 plus 2x2 is equals to a minus 2c. And if we replace this here, what I will get that 2x1 plus x2 plus x2 plus c is equals to b. So what will get 2x1 plus 2x2 is equals to b minus c, and another is that x1 plus 2x2 is equals to a minus c. So if you subtract from these two, what I'll get, subtracting this equation from this 2x1 plus 2x2, what I'll get, yeah, so we'll get x1 is equals to b minus c minus of a minus 2c. Yeah, so x1 will get b minus c minus a plus 2c. So we'll get b minus c, b minus a plus c. This is ax1. I hope this is correct. B minus a plus c. This is x1. And then what will be the x2? X2 will be, from here if we try to obtain, 2x2 is equals to a minus 2c minus x1, which is equals to a minus 2c minus b plus a minus c. So this will be 2a minus b minus 3c. What these terms are coming? Okay, so x2 is equals to 2a minus b minus 3c by 2, and x1 is equals to x1 already obtained. So x3 is equals to x2 plus c. So 2a minus b minus 3c by 2 x2 plus c. This will be 2c, that is 2a minus b minus c by 2. So these are the x1, x2, x3. So what we'll get if, so ABC is equals to look like this way. So basically what I'm getting ABC, this is equals to x1 is actually b minus a plus c whole alpha 1 plus x2 is equals to 2a minus b minus 3c by 2 alpha 2 plus 2a minus b minus c by 2, that is alpha 3. So now if at the point ABC, any f, what I have written, sorry, fi, so fi is equals to b minus a plus c. So this is clear that f1 at the point ABC is actually this one, and f2 at the point ABC is actually 2a minus b minus 3c by 2, and f3 at the point 2a minus b minus c by 2 is actually, f3 at the point ABC, that will be equals to 2a minus b minus c by 2. Why this is? This is because f1 is actually mapping every element to its first coordinate, f2 is mapping every element to its second coordinate, f3 is mapping every element to its third coordinate, and this is what we have obtained. Okay, so let me check b minus a plus c. Where is the options? Options is here. B minus a plus c is actually with these two are the only possible. First two are not correct. So these two are not completely possible. This I have to check because that's not matching. So minus a plus b plus c. So a is actually minus a plus b plus c. So other two options have to match. So first option is matching with the both of them. Another, oh okay, they have breaked it. Okay, a 2a minus b minus c, these are last two option is also matching in these two cases. So we have to check with only x2. Okay, so x2 is, what is in terms of x2? X2 is actually equals to a minus b by 2 minus 3 by 2c. A minus b by 2 minus 3 by 2c. Minus 3 by 2 by 2. So this is the correct option. This is the plus, so that's why this is not correct. A minus b by 2 minus 3c by 2. Yeah, minus 3c by 2. So these are the options. So this is, I think this is what it is, right? So this is so C option is the correct, and the first option is incorrect because they are not matching at the first place. So we already discussed those things. Yeah. So is it clear? This is interesting problem, easy and interesting. But even still, if you have any doubt, you can ask. Is this problem clear? Okay. So let me check the time. Yeah, done. So I think I'll not do anything from here. So in the next tutorial, we'll be stating from the next. And even if you have any doubt regarding old assignments which already submitted, which already deadlines was over, so you can ask here. Even if you have any doubt other than those things, even assignment problems type things, you can ask here. Maybe the current assignment I will not explicitly state the solution, but I will try to give you a hint which will help you to solve this problem. Okay. So if there is no other doubt, so I will stop here in 1 minute, few seconds, not 1 minute. Okay. Thank you, everyone. Thank you.